So what is a rear impact guard? It's a device that you bolt under the frame of a truck to prevent an underride. An underride is a car that will drive below the frame. You can imagine the damage. You want to prevent that. You put a rear impact guard. That customer had the idea to make a rear impact guard which was deployable. So you can fold it and have a higher ground clearance capacity to drive off-road, and once you're on site and you need the rear impact guard, you can deploy it. So for that system, we have few items to figure out how to design. The mounting plate has to be strong enough to sustain and attach the rear impact guard to the structure, but it must not vibrate when the truck is driving. We have to choose and size a jack which is powerful enough to deploy the system. And maybe the most critical part are the crumple zones. The crumple zones are these parts that needs to be designed so they can meet a certain industry standard from the FMVSS. The Federal Motor Vehicle Safety and Security tells that this rear impact guard must comply to a certain stiffness. If you apply a force of 100 kilonewton, the bumper must not deflect more than 5 inches, but has to absorb at least 5,650 joules of energy. So it tells you that you have to find this right challenging balance between stiffness and compliance. And from a company that don't have a lot of experience, for like this customer who had this design idea, it's really not an easy target to achieve. And if you use a classical iterative process, it can take a while before you reach to the right balance. So we have different objectives that we start the project by planning all of that. So we use an app called the Test Manager app inside the platform. So there is a lot going on the screen, so please try to not get lost and follow my laser point here. So this Test Manager app, it's a web-based app, part of the 3D Experience platform. It allows the user, usually a senior user, to plan all the tests that needs to be done. So it doesn't only fit the FEA test or the simulation test. You can also include your physical test your physical test plan. You can organize all your tests in chapters, but what I want to focus on is here. You have a test execution item that becomes an object in your database, and that object you can assign your CAD product to it. So you keep track of what tests should be done to what CAD product and who is going to do the test and choose the user. Upon that, you can add a test script. So this could be just a brief description of the step to follow. You can include your in-house PDF document, PowerPoint, whatever, all the instructions so the assignee knows what to do to proceed to that test. Once you've been assigned to such an execution, you receive a notification. Or before the notification, I apologize, you can have this kind of table review of all the requirements that you need to meet and all the test cases that you've created to make sure that everything is covered in your test plan. Once you've been assigned to a test, you receive the notification that now you have in work, so you know that you have to start working on that. That notification contains all the information you need, what FEM you need to work on, what is the CAD, sorry, you need to work on, the description, the test scripts, and you're good to go. So once you use that inside the platform, we create something called a branch. So it's the CAD will be kind of duplicated, but still connected to the original. So the analyst has its hands free to create all the CAD simplification they need to proceed to the finite element simulation. Once the assignee has done the simulation, he can share a dashboard, which is just a web page, to share what he has done, what the work he has done to validate that the crumple zone was indeed designed to comply to the standard. So this can look like this. So you have few windows, few apps. On the top left, you can review the CAD with the 3 application plates. So it's just a portion of the frame, and you find the crumple zone being here. On the bottom left, you have kind of a highlight view of the simulation result with the pushing plate the application plate pushing on the bumper. Here it's an explicit simulation because you have buckling and post-buckling behavior you want to capture, a lot of contact between the part itself, so it's an explicit simulation. You can monitor the energy, and what the analysts find out is that with that current design, we will not meet the requirement. Yes, it's stiff enough, but it will not allow to absorb enough energy. So here you can capture the results using that application. You know the steps from the script that you have to follow to make sure the design complies to the standard, and you can have a pass-fail criteria. And here we have the fail criteria on the absorbed energy. And then it becomes an issue that the engineering team has to figure out. So everything is kept, everything keeps track of the different steps of the process. So now we have an initial design that doesn't comply the criteria, but can we size that design concept so we meet the criteria? So we back to the drawing board and we reshaped the crumple zone with a parametric design using a CATIA app. So here with simple parameters like the length of the crumple zone, its width, the offset of the V-shaped plate, and the thicknesses of the plate that we use, can we find the design that would meet the criteria? So by creating the parameters, you can set the boundaries, the minimum value, the maximum value, and the step size of each parameters. Step size matters mostly for the thicknesses, so you don't create thicknesses of plates that you cannot procure, you cannot buy. Then you run the first simulation of the initial design and you set the objective or the KPIs that you want to measure out of the simulation. Here we want to keep track of the mass. It's always a good idea to try to minimize the mass. The reaction force of the force versus displacement curve, we want to make sure that we don't have a maximum which is too early, not to absorb enough energy. We want to make sure that the maximum is reached at the end. So we have enough time to absorb enough energy to comply to the standards. So we want not the maximum too early, and we want the maximum to be the latest point. So kind of change the shape of that curve. So we set a bunch of objectives here, and the absorbed energy, of course, we want to maximize it, being more than the requirement from the standard. And we used an app called Parametric Design Study. Parametric Design Study allows you to run not only one design, but to play and run all the design iteration that you are able to generate. So here is the overview of the Parametric Design Study result. Every point you see here is the result of a design iteration that are organized depending on the output that you decide to play in that window here. So here we have the latest reaction force in the x-axis, and on the y-axis we have the absorbed energy, and we need to be in that window. But we also want that the maximum force is not too early. So we have this color code that everybody can get, which is red when it's not failing, when it's not meeting the criteria, or not red if it's meeting the criteria. And here you have the summary of the main result for each design iteration. Plus you have a center view to represent what are the design iteration. So here, by just specifying a quick parametric optimization, it will tell you that, and what it told us was that that initial design with the 50 design iteration that has been generated, among the 50, none of them were meeting the criteria. So it's a very powerful tool because you will not lose time, you will not spend months trying to find an iteration that fits, but in less than a week turnaround time, you'll figure out that that concept doesn't work because it buckles too early and it's not stable enough to withstand to comply the standard. So back to the drawing board, and we thought of a new concept, which is 2 ellipses. Can we shape 2 ellipses flat plate, which are quite cheap to manufacture, and find the right size so we meet the requirement? So we create a revision from the design and we replace the initial crumple zone by this new concept. And we proceed to the same workflow, but instead of having just the sub-assembly of the bumper, we included all the assembly because we realized that the boundary condition of that in that tube were a bit too restrictive. So using the full assembly, we have 3 different analyses with 3 different positions of the application plate to make sure we cover the full scope of the standard. And we do the same approach. Instead, we don't use parametric design study, we use process composer, which is eyesight included in the platform, in the 3DX. And we have a simple design of experiment algorithm that is going to be driving a physics simulation, which is our simulation of the test. And we can use a model parameter tool to plug the requirement that has been captured from the standard at early stage using the test manager app. We can capture these requirements and link them in the process. So again, for traceability, you know that that process has been executed following the requirement that has been captured in the test manager plan. And here it's the result, what it looks like. So again, you see every point is one design iteration. Here we have 100 of them. You see the different shape that the ellipses takes and the summary of the result on the right. And you see that some iteration has no red, meaning that we could meet the requirement. We executed all this analysis on the cloud over a weekend time. So we computed 2 analyses at the same time on 8 CPUs each for a total of 65 hours of compute. So on Monday morning, you arrive at the office and you have 100 design iterations to digest and to analyze. Please be reassured, you don't have to open 100 ODB file or result file. You can just post-process the meaningful data because you have all the result sensors that you've created. So by just looking at that chart, you can post-process and find the meaningful information. So here, good news, in that window here of point, we could find several designs that was meeting the requirement. Another way to map the requirement is to use the result analytics app. You're going to generate a lot of data with the 100 design iterations. So to post-process the results and to make the data talks, the result analytics apps allow you to extract a lot of statistical data to study the sensitivity. So you not only find what design is going to meet the criteria, but you also have like an overview, an understanding of your design. What are the meaningful parameters that will impact the most, the KPIs, the meaningful results? So in that result analytics app, you can find the requirement that has been created as an object in your database and link that object to the sensors or the main output from your simulation, from your process, your design of experiment. And that will help you to rank the designs from the best to the worst. And you can, this is the geek part, nerd part of the presentation, you can create a lot of tables, graphs, plots, comparison to learn about the sensitivity. I will not bother you with that, but it's very powerful to learn about what matters and what's not. And you can compare the best design to find what is going to suit your problem. And finally, we did proceed to the validation case after selecting our best candidate. And we could see here a totally different shape of the force versus displacement curve that was steadily increasing until we reach the target from the standard with more than 5,000 joules of absorbed energy. So using that approach, that Dassault system called ModSim, which is a contraction of modeling and simulation, because you have everything included inside the same platform, you have the parametric optimization, the parametric design from CATIA, allowing you to update and generate the design automatically. And you have your FEM and your scenario link to the CAD because you are using the same graphical interface with no file transfer. You are unlocking this type of workflow in which you let the algorithm find the design for you. So using that approach, it took us a week time to figure out a viable solution for the customer. And without that approach, by using classical iterative process, I honestly don't know how long it would have taken us to come to that solution. So now that we have a workable solution, a viable solution, we can capture the result again inside this and from the test manager app. After capturing the result, we have the pass criteria, and we can attach the validation simulation, the simulation object that was used to validate and confirm that that design would comply to the standard. And by doing that approach, in the background, you also have your Gantt project management window that is populated automatically every time you create a task, you assign someone to a task. So in the background, you have the project management aspect of it, which is handled for you. And again, with no additional work, just because you linked the right object to the right simulation tools, you have this traceability app, the relations app that is become my favorite, to find out where you are, what simulation is attached to which CAD, using which FEM, having which part as a subassembly. Do you have a subassembly attached to a simulation? What is the material that was used in the part? You can find out with this very intuitive window all of your data, handling the revisions, the duplicate, so you can have a clear view of what is the latest design I have to work with. This is how I use the relation app as an analyst. As a test manager or project manager, the same application can be linked upward from the simulation. So from the simulation, you can find the product that has been simulated. That product is created because we had an issue of the crumple zone not meeting the criteria. That issue has been raised by that assignee. You cannot hide from your responsibility anymore. And then that has been driven by a test manager from the requirement from the standard that has been studied. So all this traceability is kept for you in the background.